What's up, asparagus hunters? It's Miss Sorensen back with video 19, Monty Hall problem. It's actually a pretty famous problem, and it's pretty close to my heart because I remember being in a really large building one time with tons of computer scientists. I was interning at a computer software company back my sophomore year of college. And they asked this question, and in a room of many, many, many people, I raised my hand and I solved it. And people thought I was pretty cool after that. I was pretty cool among the computer science nerds. It doesn't have to do with computer science. I hope you enjoy it. I think it's a pretty fun problem. All right, so here's the problem. You are on the Monty Hall show, and you are presented with 3 doors, A, B, and C, and only one of which has something valuable to you behind it. The others are bogus. And typically this is done with, there's 1 car behind one of the 3 doors, and there's 2 goats. And I know you guys in Manson really like farm animals, but you want to assume that people don't want goats. I know that's a little foreign to you guys. You do not know what is behind any of the doors. You choose door A, right? You choose door A. So you choose this one right here. And Monty Hall says, oh, okay, you chose door A. Let me show you that door B has something else behind it. And usually they show you a goat, right? So he says, okay, you wanted door A. That's cool. But did you know that there's a goat behind door B? Or there's nothing behind door B that you want? And then they say, hey, do you want to switch to C? Do you want to switch here, or do you want to keep your original choice? Well, it's a little tricky, right? You're like, well, I really liked my original choice, but now do my odds increase if I swap doors? And if so, by how much do they increase? So, if we were in class, we would play this with some fake money, and it'd be quite a bit of fun. But let's actually just play right here. So let's say you chose door 1, okay? And they say, hey, there's a goat behind door 2. So do you want to keep your door 2? Or do you want to keep your door 1, or do you want to swap to 3? Well, you're kind of superstitious, right? You're like, well, I really like door 1, so let's stick with door 1. Oh, and we won a car. Congratulations. All right, let's try this another time. Okay, let's say this time we chose door 3. And they say, hey, there's a goat behind door 1. And we said, we really like door 3. Let's stick with door 3. So I stick with door 3. I got a car again. All right. Let's try this again. All right, let's pick door 2. They show me there's a goat behind door 1. So I'm going to say, hey, I'm going to stick with door 2. Oh, this time I lost, right? I'm a loser. Okay, another time. Let's pick door 1. Should I keep my door 1 or should I swap? Well, let me keep my door 1. I want a car. All right, let's see what we got here. I want to pick door 2, and they say, hey, there's actually a goat behind door 1. I say, I like door 2. I'm going to stick with door 2. Uh-oh, I lost. I got a goat. So the question is there actually a better solution here? It looks like we kind of won some and lost some by sticking with our original door. So far today, it's kind of early in the morning here, so there's not tons of people who've played this morning, but it looks like of the people who switched, 77 people won, which is 62%. And of the people that didn't switch, only 24 people won, and we're actually, I think, 2 or 3 of those people. And so out of everyone who's played this game today, 33.3% who didn't switch won. And so looking at these numbers, do you see some sort of a common number between the two? Is maybe didn't switch 33% and what's going on here? Do you think it's going to be 1/3 and 2/3? Do you think it's going to be 1/2 and 1/2? What do we think the actual probability is of winning if we switch versus don't switch? Well, let's actually calculate it. And this does certainly get a little bit confusing, but let's see if we can get this understood here. So let's assume that the car is behind door A. And we don't know this, but we're trying to come up with all the possible situations. So let's assume right now the car is behind door A. If you originally choose door A, do you want to switch or do you want to change? Oh, sorry, do you want to stay or do you want to change doors? Well, obviously, if you chose door A and the car is behind door A, you want to stay, right? You wouldn't want to change your door because you chose the right door. You wouldn't know it, right? I'm just saying this is a possible situation, but in theory, you'd want to stay in that situation. All right, what if you chose door B and the car is behind door A? Well, in this case, if you chose door B, Monty Hall would show you that the goat is behind door C, and you would be asked, do you want to switch or do you want to change doors? And if you chose door B, but the car's behind A, you clearly want to change. All right, let's go through this a little bit faster. If you chose door C and if the car's behind A, you are going to want to change doors. Again, you don't know this, but this is in theory. We're trying to go through all the situations. Well, what's another situation? The car could be behind door B, and if you chose door A, they'll show you the goat behind door C, and you're going to want to change. If you chose door B and the car is behind door B, in that situation, ideally, you would want to stay with the door that you originally chose because you guessed the first one correctly. And then if the car is behind door B and you chose door C, they'll show you the goat behind door A, and you'll want to change in that case, right? Because you don't want to stay with door C if the car is behind door B. All right, now last situation is the car would be behind door C, and if you chose door A, you would want to change. If you chose door B, you would want to change. If you chose door C and the car was behind C, you would want to stay. Okay, so what's the probability of winning if you stay with your original door? Well, how many possible situations are there? There's 9. And where do you want to stay? You want to stay here, here, and here. That's 3 out of 9 is 1/3. Okay, which is about what, 33.333%. And then, what's the probability that you should change doors? Okay, well, that's going to be out of 9 again, but we want to change 1, 2, 3, 4, 5, 6 of the times out of 9. 6 out of 9 becomes 2/3. Okay, and so we kind of looked at those percentages earlier, and this ends up being 33.3% chance that you win if you stay with your original door. But if you change doors, this becomes 66.6% chance of winning. So you double your odds of winning if you change doors. And it's a little bit, I think, counterintuitive, because wouldn't you think in a situation here, let's say I pick door 1, and now I know, okay, there's a goat behind 3. You would think that if you went to 2, you would have a 50-50 shot, right? Because now you're down to 2 doors. One has a goat and one has possibly a car or a goat in it, right? But that's a 50-50 chance because you already know what one is. But that's not actually true because you've got dependent probability going on. You have an all-knowing host who purposely shows you a goat behind door 3. And it's a very interesting problem because a lot of people say you have a 50-50 chance to change doors, but in reality, it's actually a 66.6% chance, and you're doubling your odds by changing doors. And just a quick reminder that you don't always win when you change doors. Sometimes you win when you stay with your original, which we did win on a couple occasions, staying with our original door, but you have a higher odds of winning if you change your door. All right, hope you found that interesting.